Okay, so we were studying weak star topology. I give you an assignment. So if X is a Banach space which is separable, then the unit ball of X star is separable with respect to weak star topology. Okay. So I mean, sorry, forgot to say. That's not. I'm not saying something. The unit ball of X star is metrizable. Sorry. Of course, if it is metrizable, it's compact, and it's metrizable means it's separable. So you have to define a metric with respect to weak star topology on X star, on the unit ball of X star. So if X is separable, then the unit ball of X star is metrizable with respect to weak star topology. So you take a sequence Xn contained in X, dense, then you just define 1 by 2 power n summation n equal to 1 to infinity d of so you want to define d of phi and psi. I mean, you want to define a metric in the unit ball of X star, you just define it to be phi of so this is norm of phi of xn minus a of xn. I think this will work. Okay. So you define the V metric and show that this is a metric, and so some convergence in this matrix is equivalent to saying convergence in weak star topology. So that will prove that the unit ball with respect to weak star topology is metrizable. So if it is a metrizable, we do already know it's compact. So a compact metric space is separable. So it will follow that the unit ball of X star is separable. I mean, it's a compact metric space. Okay, so this is one assignment. So when X is not separable, then this is not true. That's what I want to say. So let X equal to, this is example, at X equal to L infinity, which is not separable, of course. So then I want to say that, the unit ball of dual of L infinity is not weak star. I mean, it's not metrizable. So how do you do that? So let pi n from L infinity to C be the projections, okay, the coordinate projections. That is pi n of any xk equal to xn. Okay? Any xk in L infinity is xn. So it's just the coordinate projection, nth projection on that. So if then pi n, all this pi n equal to infinity is a subset of unit ball of L infinity star 1. Okay, the unit ball of L infinity. Because all these things have norm equal to 1. And that is in the unit ball of L infinity star. Okay. So if you have any doubt, you just ask me, stop me and ask me. Okay. So I want to say that this L infinity, this is compact. Those compact Hasdar. But this is not metrizable, I want to say. So if it is metrizable, then it is sequentially compact. So I want to say it is not sequentially compact. That is, this pi n does not have a converging subsequence. That's what I want to say. So the claim is pi n does not have convergent subsequence. So I want to say that if you take any subsequence, that's not convergent. That's what I want to say. So this claim will imply L infinity star 1, the unit ball, is not metrizable. If it is metrizable, then it is a compact metric space. So every sequentially compact. So every sequence will have a convergent subsequence. So that is not the case here. Okay. Okay. So why pi infinity? So suppose now the proof of the claim. So suppose pi n k is any subsequence of this subsequence. So you have to say that this is not weakly convergent. So it's very easy. So define xn contained in maybe xk contained in L infinity by x n 2k equal to 1, okay, and x k equals -1 otherwise. Then pi nk of this xk equal to xnk, of course. But xnk, I mean, this is xnk, and xnk is not convergent. Okay, because I mean, xn 2k is +1 and it's -1 otherwise, so it's not convergent. Okay, but then this is what weak convergence means. This implies pi and k is not weakly convergent. It's not. Sorry, weak star convergent. It's not weak star convergent. Okay, so that's right. So this implies L infinity is not metrizable. This implies this implies L infinity star 1, which is compact. It's not sequentially compact. Compact. This implies not metrizable. Okay. It's fine. Okay, so this is just an example. The assignment is to say that if x is separable, then x star dual, I mean the unit ball of the dual is metrizable. So which is not the case with L infinity. Okay. So now I want to shift to another topic. So I want to, okay, yeah, ask me.
Is the converse to the assignment too?
Say it again.
Is the converse to the assignment too?
Converse to the assignment is if
that is, if the unit ball is metrizable with respect to weak star topology,
if the unit ball is metrizable, then it is weak star compact. So I mean, then it is. I think it should be true, but I don't see a proof. I mean, if you work hard, I mean, I don't know for sure, but you have to work. I mean, you can try. Okay.
Okay,
so,
sir.
So I'm not sure about it. I think it should be true. Okay. It's just a guess. I haven't seen it. Okay. Okay. I mean, I think though every non-separable, if X is not separable, then it's dual, it's not metrizable. I think that is true, always the case. So it should work. Okay. I mean, you can prove that way. If X is not separable, then the dual, the unit ball of the dual is also not big star metrizable. Okay. So I think that is true. So from that, I mean, the same kind of thing you can somehow work it. Okay. So the next I want to talk about. So in the exam, there was one question. I was very disappointed. No one really solved that question. So in the exam question, okay, exam problem. I mean, which is just a easy. Some people solved it, but through a very indirect way. But it's some people try to use uniform boundedness principle and all. It's just a closed graph theorem. So, I mean, in my exam, the part A is basically questions which uses some of the argument we have gone through in the class. Okay, it is just a slight, it's just a slight modification of some of the arguments we have seen. So that's why, I mean, that's what all the problems in part A is. So in the class, we have proved some theorem, something like this. If T equal to T star, and then we prove if T equal to, I mean, if you have any operator, which, I mean, we proved some theorem, something like this in the class. Okay, if T is an operator, T is some operator, need not be bounded. T is some operator, T is from H to H, okay, linear. I will erase this. We proved that and Txy equal to xty for all xy. Then T is bounded. We proved this. Okay. It is basically the same problem, which is this problem. If, this was proved in the class. Okay. Last semester class. Okay. So the exam problem is if exam problem. This is exam. Is if T is from some x to y, xy Banach spaces. Okay. Banach spaces. And there exists a S from y star to x star, such that which acts like an adjoint. So the problem is the existence of adjoint implies it's bounded. Okay, you don't assume both T and S are bounded, but the adjoint exists. There is a, I mean, adjoint property means this kind of property. So adjoint exists, then it is actually bounded. That was the question. That is phi of T equal to S of phi. Okay, that is you apply X for all X in X. Then T is bounded. Of course, that will imply S is also bounded. Okay. And this is just closed graph theorem. I don't know why nobody thought about it. So this is just if so proof if xn converges to x and txn converges to y, okay, then phi of y, phi of tx, phi of tx equal to phi of t, phi of y, phi of y equal to phi of txn, because txn converges to that, and phi is a continuous linear function, and which is equal to s of phi of xn. Okay. Now that is equal to, I mean, this is equal to limit. I have to put a limit of this. So this, and which is equal to s of phi is a continuous linear function, so which is equal to s of phi of x, and this is equal to phi of tx. This is true for all phi in x star. Okay. This implies y equal to tx. This implies t is bounded by closed graph theorem. So this is just that. Okay. So the reason I'm saying is we want to use a similar closed graph theorem, similar kind of thing to prove the following theorem. So this is clear. Okay. This is just an application of closed graph theorem. So you remember this question in the class, in the exam. Okay. So this just says that if some operator T, which you don't assume it's bounded, if it is adjointable, then it is bounded. Okay. That's what this says. Okay. So now I want to prove the following proposition. T is an operator from H to K, I mean, this can be proved for this can be proven for Banach spaces also, but I don't want to complicate it. Okay, the existence of right triangle and all those things. I want to prove it for Hilbert spaces. Okay, HK Hilbert spaces. Okay, it's just a linear operator, linear. Okay, then one T is norm. I mean, so we can, so H is a Hilbert space. We can put two kind of topology. One is norm topology, otherwise weak topology. Okay. So with respect to, I mean, the weak, we consider, I mean, whichever the topology we consider, we write the continuity depending on that. So T is norm. I mean, if you put norm topology in H and norm topology in K, that's what I norm continuous. Okay. That is equal to, then the following are equal. Okay, let me just say these two are equal. First prove this. T is norm continuous is equivalent to saying, but this one is easy, I think. T is norm weak continuous. This is just an application of closed graph theorem. So, and also it's maybe the one statement one. Statement two is T is norm. I mean, all those things are equivalent. That's what I want to say. But I want to prove this equivalence and then this equivalence. T is norm continuous is equivalent to T is weak continuous. I'm sorry, my handwriting is very bad, but I can't help. Hope you understand this. Okay. So first proof of one. So if T is norm continuous, clearly T is norm weak continuous. This way is clear. I mean, if some xn is converges, xn converges to x in norm, then Txn converges to T, Txn converges to Tx in norm, so it converges weakly also. So this way is clear. We have to prove only this way. But then this way is also clear by closed graph theorem. This way follows by closed graph theorem. That is, if xn converges to x, if Txn converges to ui. Of course, closed graph theorem is true only for non-linear space, not for weak topology and all those things. Okay. So if xn converges to x and Txn converges to y, okay, then if xn converges to x, we have assumed that it is norm-weak continuous. That's what this proof is. This way, we are assuming T is norm-weak continuous. Then we want to prove that T is norm continuous. Okay. So since T is norm-weak continuous, xn converges to x in norm. This also converges in norm. Okay. This implies that, Txn converges to Tx in weak topology. Okay. But then, since Txn converges to Tx in weak topology, what does it mean? This means phi of Txn converges to phi of Tx. Okay. For all phi in Y star. Okay. Right? That's what this means. Okay. On the other hand, Txn converges to Ty. So this implies that Txn this converges to phi of Y also. Okay. Since Txn converges to Y in norm, phi of Txn, because phi is norm continuous, phi of Txn converges to phi of Y. These things implies phi of Txn, Tx equal to phi of Y. This is true for all phi in Y star. So this implies by Hahn-Banach theorem, this implies that Tx equal to Y. So by closed graph theorem, it follows. We are going to apply whole closed graph theorem again for 2. Well, if you have any, if I am going fast or if you have any problem, you stop me. Otherwise, I will continue fast. Okay, because I don't see anyone. Okay. 2. We are assuming 2 is T is norm continuous. We want to prove T is weak continuous. Okay. So assume. So we want to prove this way. So assume T is norm continuous. Then we want to prove T is weak continuous. So suppose, so since it is weak topology, we have to take net, but that's okay. It's just some notation. We are not going to really use the property. Suppose x lambda converges to x weakly. We want to prove weak continuous. So we are assuming x lambda converges to x weakly. We want to prove that tx lambda converges to tx weakly. Okay. Okay. So to that is x lambda y. I mean, it's weak continuous in Hilbert space, so it's just inner. I used phi there, but it's just inner product here. Sorry, this has to be y I wrote, but it should be k star. I'm sorry. Then x lambda y converges to xy, okay, for all y in H. That's what it means by it converges weakly. Now Tx lambda, we want to prove that Tx lambda converges to Tx weakly. That's what we want to prove. Tx lambda z, okay, the z is in k, okay, which is equal to, but then T is bounded. I mean, T is norm continuous means it's bounded operator. So the bounded operator means there exists adjoint for that. That we have proved. Any bounded operator has an adjoint. Okay. So this is equal to x lambda T star z. Now x lambda converges to xy, x lambda y converges to xy for all y. Okay. So this converges to x T star z. Okay. So, but this is equal to Tx z, right? So this Tx lambda z converges to Tx z. So this just means Tx lambda converges weakly to Tx. Okay, so we have proved. So that is T is weak continuous. So if some T is norm continuous, then it is weak continuous. Now you want to prove weak. I mean, this is the now T is weak continuous. Then we want to prove T is norm continuous, but that is just again closed graph theorem. So suppose T is weak continuous. Okay. We want to prove T is norm continuous. So by closed graph theorem, it's enough to prove that the graph is closed. So suppose xn converges to x in norm and txn converges to y in norm, then we want to prove that y equal to tx. That's what we want to prove. And then that is clear. Xn converges to x in norm. This implies xn converges to x weakly. Okay. But then since T is weakly continuous, this implies that Txn converges to Tx weakly. But then Tx converges to Y weakly. I mean, weak limit is unique. Okay, so this implies we have already gone through that. So this implies we have already gone through that proof. So this just implies that Y equal to Tx. So again, by closed graph theorem, implies T is bounded, which is what we mean by norm continuous. Okay. So what have we proved? We have proved that if you put norm topology here, that is equivalent to saying you replace this norm topology here and weak topology here, or weak topology and weak topology, that is true. But it is not the case that T is norm continuous will imply T is weak norm continuous. That is not. So those operators which satisfies that property is what are called compact operators. So we will come to that. So far everything is okay.
Yes, sir.
Okay. So, going fast. So before that, I want to introduce some new topology on the space of operators. So in the space of operators on Hilbert spaces, this can be introduced in Banach spaces also. But on this way, but we have already seen, I have introduced in the last semester. So we want to introduce what is called a strong topology. This name strong topology is misleading, but unfortunately that is what being used in the literature. So H is a Hilbert space. Let us take Hilbert space. So then we say T lambda a net contained in B of H. Okay. Then T lambda. Okay, before that I want to say something. Sorry. Okay, let's take a net. Okay, then T lambda is a net there. Okay, such that T lambda x converges to Tx. Okay, in norm, of course, in norm. Okay. I mean, it's a point-wise convergence. T lambdas are operators. Okay. So usually when we consider operators, we will consider the convergence in norm, operator norm. Okay. But then this is point-wise convergence. T lambda x converges to Tx in the norm in H, not in the norm in operator, not the operator. Okay. Then T is bounded. Okay. This we have seen in the last semester. This is because of uniform boundary principle. Okay. Then we want, then T is bounded. Why is T bounded? Then because Tx, non Tx is less than or equal to. So that is because of uniform boundary principle. So non Tx is less than or equal to T minus T lambda x plus non T lambda x. Right? Okay, so now T minus T lambda x is, I mean, given any x for x is in the unit form. X is in H and norm x equal to norm x is less than or equal to 1. Okay. So now the T minus T lambda x that goes to 0. Okay. So that can be made as small as you want. Okay. Then this can be made less than epsilon. Now this T lambda x is bounded. Norm T lambda x is bounded in lambda. So by uniform boundedness principle, boundedness principle, norm T lambda is bounded. Is less than quality. So that whole thing is less than or equal to. This is some, you make it, I mean, the other thing does not matter. That is less than epsilon, but that will depend on epsilon. T, so should we make that also less than epsilon? That epsilon will depend on the epsilon. So no, that's okay. We are taking that is less than, I mean, that will go away because that is less than 1, no? So that is less than, I mean, can make that less than epsilon plus this is m times this m. I mean, this is norm, this is less than norm T lambda times norm x. Norm T lambda is less than, yeah, so this is m plus epsilon. So this implies T is bounded, norm T and T is bounded. Okay. Anyway, take it. So if you have a T lambda, if you have a net T lambda which converges pointwise, then the limit is also then the limit is also bounded. Okay, this is what is called strong convergence. So we say T lambda converges to T if T lambda x converges to Tx for all x in H. So this is what we call as strong topology. This topology is what is called strong topology. And this is what is called strong convergence. Okay. So we will come back to this strong convergence. There, I mean, I will show you examples where things converge strongly, but they don't converge in norm topology. They are going to immediately see something. Of course, this thing happens in infinite dimensional. This is not coming. For finite dimensional, everything will coincide. Okay. So I want to prove the following proposition. No, before that, I want to introduce something. Maybe I will prove the following proposition. First, then I will introduce that. Okay, so there exists. Okay, I will introduce some notation and we'll define something. So definition. T is an operator from H to K, all Hilbert spaces. Okay, whenever I write H and K, they are Hilbert spaces. Okay, H to K is a finite rank operator. Is finite rank if T of H is finite rank. The range is finite dimensional. Okay. So let's define this T of H. I mean, this is finite dimensional operator from H to H. Okay, all T of H to H. H to H, T is finite.
Sir, in the definition of finite rank operators, you also need to mention the continuity, right? I mean, it might happen that this range is finite dimensional, but the operator is not continuous.
No, I think it will follow. Why?
No, like we have non-continuous functionals, right? That's an example.
Sure. Linear functionals are like correct. So T is in. Sure. Okay, so this is contained in P of H. So T is, yeah, we are assuming bounded operators. Then that's finite rank if the range is finite. Since it is defined on infinite dimensional, so we have to, even one dimensional can be invoked. Yeah. Okay. So the one thing we want to see is this. This is certainly a linear space. Of course, if you have two finite rank operators, then the sum is finite. Scalar multiple of finite rank operator is finite rank. Further, it's also an algebra. If you have product of two finite rank operators, finite rank, but more than that, it's an ideal. Okay? That's what. So it's clear that let me write it. So BFH is a two-sided ideal. Ideal in BFH. BFH is an algebra. We already know what is an algebra. We have seen Schoenweister's theorem. So an algebra is just a ring as well as a vector space. Okay? And of course, which satisfies distributive law and all those things. So BFH, I mean, we can multiply operators in BFH, and so the BH is the BFH finite rank operators in a is an ideal, two-sided ideal. That is clear. If you have a S in BFH and T is in B of H, okay, then ST of H, which is equal to, I mean, T of H is again contained in H. So this is finite dimension. Okay? This is something which is contained in S of S. S is finite, which is contained in H of H, which is finite dimension. Similarly, T of SH, of course, any linear operator takes finite dimensional subspace, finite dimensional space to finite dimension. So this is finite dimension. This is also finite dimension. So this is clearly a two-sided ideal. So, but I want to say that it's also what is called a star closed ideal. That is, if T is finite rank, then T star is finite rank. So we want to prove the following. T is finite rank, then T star is also finite. So to prove that I need something. So maybe this is a general proposition. So maybe I call it a lemma or lemma. It's not even lemma. This is a general proposition. So let me call it proposition. I mean, I will use this proposition to prove this. So T is any operator in B of H. Any operator in B of H. Then H is equal to range of T. But it need not be closed. So I take the closure direction kernel of T star, which is closed. So kernel of T star. Okay. This you must have seen in finite dimensional linear algebra. Okay. So, but I mean, this is an orthogonal direction. Okay. So, proof of this proposition. We only have to prove that. I mean, if you have any subspace M, then H is equal to M direction M per. We have seen that. So we only have to prove that these two, I mean, the orthogonal complement of range T per is enough to prove range T per. I mean, you can take the closure, you need not take the closure because the if perp is same, okay, is equal to kernel of T star. That's what we have to do. Okay. So how do we prove that? If T is in one way, if T is in not T, X, element X. If X is in range T per, that means X Ty equals 0, which implies T star X Y for all y H, which means T star X Y equals 0 for all y in H. Okay. But then this implies T star X equals 0. This implies X is in kernel of T star. Okay. On the other hand, so we have proved that, so this implies, so we have proved that range of T is contained in kernel of T star. Okay. We want to prove the other way. So suppose some X is in kernel of T star. The other way is also clear. Then that is T star X equals 0. It implies T star X Y equals 0 for all y.
So the above implications are just Stephen only, right? So it is obvious. I mean, the implications which you have written for.
Yeah, that is what I'm going through. You are right. So that's what I'm writing it again. It's equal only. Correct.
Oh.
Yeah. So that's why that is equal. So that's what I'm writing. Correct. Sorry. Yes, you have said that is clear. So that's what I'm writing it again. So maybe we can just go through there itself. But if that is the case, I mean, of course, if something vanishes on the range of T, then it vanishes on the. By continuity, it will vanish, and the inner product will vanish for the closure also. Okay. So other ways also. Okay. Anyway, so it's clear. You can see that this is true. This is an easy exercise. Anyway. So from this, I want to prove the proposition. Now, proof of this proposition. Okay. Proposition 1, proposition 2. Now, proof of proposition 1. Now we know that H looks like what? Range of T direct sum kernel of T star. But here I'm not writing closure because T is finite rank. Okay, T is finite rank. Okay, then range T is a finite dimensional subspace. I don't need to take closure. Okay. So this implies T star of H equal to T star acting on range T, then T star acting on this direct sum. It's, I mean, it will just look like it will vanish. I mean, it will. I mean, any element in H will look like some X direct sum Y, but it will vanish on Y. So this is equal to T star of TH, okay, which is finite dimension. So this implies T star is also in BFH. Okay. So these things say that BFH contained in, so this is over, contained in B of H is a star closed. Star closed means T is there, T star is also there. Star closed two-sided ideal. Okay, so finite rank operators are two-sided ideal. Okay, so now I want to prove an important proposition. That proposition BFH is dense in B of H in the strong topology. It's not true in norm topology. For example, I mean, you can't approximate every operator by finite rank operators, which we will see anyway, because they are all compact operators and all operators are not compact operators. Okay. B of H is dense in B of H in the strong topology. Okay. So, I mean, this thing can be proved for, we are going to consider all the spectral theorem, we are going to do it for separable Hilbert space. We can do it, I mean, you can complicate it by taking nets of finite subset and all those things. And I mean, we can do it, but it's the same proof. Okay, so there is no really difference in the idea. So I will take it to be H to be separable. Okay, so let's assume H is separable always. I mean, this is true for non-separable Hilbert space also. Just to make life simple, we are taking separable Hilbert space so that we can use sequences. Otherwise, you can take nets. I mean, nets of all finite subsets. Okay. So first claim is maybe first lemma. I will prove a lemma and then come to this proposition. There exist projections. There exists a sequence of projection. Sequence of projections Pn, finite rank projection. There exists sequence of finite rank projections Pn, okay, contained in B of H, of course, such that Pn converges to identity strongly. Okay. Proof of lemma. And this is just clear. Let as you can see, orthonormal basis. As you can see, if this is not finite, I mean, this is if H is not separable, then you have to take an appropriate projection. I mean, you will P lambda. You can take a P lambda where let me define where Pn equal to span projection onto span. Of course, every subspace defines a projection. So I just define the subspace. Projection onto E1 up to En. Span of this. It's just a finite dimensional projection. If you want to if you want to take finite net or something, then for every finite set you take those orthonormal, subset of the orthonormal vectors, subset of that corresponding to that finite set. Here we are taking up to the finite set 1 up to n. Okay. So, okay. Then for that x is in H and the x equal to, then x will look like that, n equal to 1 to infinity x en. Okay, for this orthonormal basis, then Pnx equal to summation k equal to 1 to n. Okay. There is this finite sum. Now Pnx minus identity times x, which is this norm, but it's Hilbert space, so I take norm square. This is equal to summation k equal to n to infinity. We are just subtracting the sum up to n. So the n to infinity x e k e k. But then this is equal to x e k mod square summation k equal to n. And then this goes to 0 as n goes to infinity. You know that's a converging sum, L2 sum. So we have already seen.
Sum starts from n plus 1, right?
Sum starts from n plus 1. Okay, this goes to 0. Okay, it's just a tail I want to do. So this goes to 0. So this implies, this is what it means by Pn converges to identity strongly. Okay, a strong topology. Okay. So that is the lemma. So we want a proof of the proposition. What is the proposition? Proposition is B of H is still dense there. So you take any T in B of H. Okay, then P and T. So the strong topology has the following property that is another observation, maybe just an observation, maybe a lemma. I'll write it just a lemma. This is true for net even, because strong topology is a non-metrizable topology, so we have to use net. Okay, so if T is in B of H and S lambda converges to S in strong topology, okay, there is pointwise convergence, then Ts lambda converges to Ts and S lambda T converges to S lambda T. Okay. This is just clear. Proof. Ts lambda x, okay, converges S lambda x converges to strong topology means S lambda converges to Sx, S in the strong topology, S lambda x converges to Sx. Then certainly if you multiply T is continuous, so Ts lambda x converges to Tsx. That is clear. Okay. One way is clear. The other way is S lambda Tx will converges to Stx, because this is one such vector. Okay, so it's clear. This statement is just obvious. Okay, so strong topology is continuous with respect to if you fix one T and then it's the individual products. Okay, it's not continuous. It's not actually continuous with joint continuous, not joint continuous with respect to product. That we will see later. We may not see. There is a counterexample, but slightly complicated. You can look at similar to the Okay, so that is true. Now the proof of the proposition follows immediately. Proof of proposition: T is in P of H. Then take Tn equal to Pnt. Okay. So Tn converges to P strong. So that's what it means by finite rank operators. We are just, the claim is finite rank operators are dense in B of H. Okay, you take P and T, that will converge. Okay. So we have proved that finite rank operators are dense in B of H. But then it's, I mean, in the strong topology, but it is not dense in the norm topology. So the closure of finite rank operators is what is called compact operators. So for that, I want to prove the following proposition. Proposition T is an element in B of H. Okay. Then the following are equivalent. One, T is in the B of H closure with respect to norm. Okay, it's with respect to operator norm. It's not the strong operator. With respect to operator norm. Second thing is T restricted to H1. This is just unit ball. Okay, unit ball of H is weak norm continuous. Put weak topology in the ball, and of course norm topology in the range. It is continuous with respect to that. The third thing is T of any bounded set. I mean, you can replace that by any, I mean, it's just the closed ball. H1 is the closed ball. H1 is the closed unit ball. So T of the flow H1. Let us take H1, but then it is true for any bounded set. Okay? T of bounded T of H1 is compact with respect to norm topology. These three statements are equal. We assume H is separable so that we don't need to. We can use nets otherwise. I mean, every net has a if it is a compact topological space, compact Hausdorff topological space, need not be metric space, then every net has a convergent subnet. But we will not worry about that. Let's assume H is separable. Throughout this course, we will assume H is separable. We will use sequence. Okay, proof.
Sir, so the third part of this proposition, should that be T of H1's closure is compact or only this is compact?
That's what I was thinking, but I think it is no. It is, this is compact. There is no need for closure. It will be closed automatically. It just follows from 2. Okay. Let's see. No? Okay. So 1 implies 2. So T is in the closure of finite rank operators. Then T is weak norm continuous. Okay. So T is in the closure of P of H with respect to norm topology. So there exists a S, a finite rank operator H, such that, so it's I mean it approximates in the norm topology, so such that T minus S is less than epsilon. Okay. Okay. Now we want to prove that T is weak norm topology. So suppose X lambda converges to X weakly in the Hilbert space. Okay. Then we want to prove that Tx lambda converges to Tx in norm. Okay. So Tx lambda minus Tx. We want to consider this. But then this is less than or equal to T minus S x lambda. So let me write the whole thing. Tx lambda minus Sx lambda plus Sx lambda minus Sx plus Sx minus Tx. Okay. This is less than or equal to, once again, so we want to prove that x lambda converges to x. So this, we are assuming that it is in the unit ball. Okay. So x lambda contained in H1. Okay. So this is less than or equal to T minus S. Norm T minus S, norm x lambda is less than or equal to 1. So this also x lambda converges to x weakly. Okay. But then the unit ball is it's weakly compact. There is no weak. Hilbert space is reflective, so it's weakly compact. So that is also in the, that's also in the unit ball. So I'm just saying 2 times T minus x. These two things I'm just writing it as 2 times this. Okay. This is okay. 2 times T minus this plus Sx lambda minus Sx. Okay, that's what we have. These two I have written it as 2 times 2 into T minus x. T minus x. Because norm x lambda is less than or equal to 1. Norm x is less than or equal to 1. Because of. Okay. Now Sx, S is finite rank. So range of Sh is finite dimensional. And we have seen, finite dimensional, weak topology and strong topology, weak topology and norm topology coincides. Okay. So Sx, where on this space, Sx lambda, so Sx lambda, Sx, these are all in Sh, which is finite dimension. We know that, but then we have assumed that, what have we assumed? Finite dimensional. So S is bounded. S is bounded. That is, it's norm continuous. This implies S is weak continuous. We have proved that. Okay. Continuous. Now x lambda converges to x weakly. Okay. So this implies Sx lambda converges to Sx weakly. Because S is bounded, S is norm continuous, but we have proved that norm continuous is equivalent to weak continuity. So x lambda converges to x weakly, that's what we have assumed. So this implies Sx lambda converges to Sx weakly. But then since Sx is finite dimensional, these are all contained in Sx, which is a finite dimensional subspace. Okay. Since Sh is finite dimensional, Sx lambda converges to Sx in norm. So that thing goes to 0. Okay. This thing, T minus S is less than epsilon. So you can choose, you can find it. This is less than epsilon. Okay, this is less than 2 epsilon. Plus you can make it less epsilon for lambda greater than or equal to lambda. You can choose a lambda on such that. Okay. So we have proved that this implies what? X. T is weak norm continuous on the unit ball. Right? Is okay?
Yes, sir.
Okay. If it is not okay for anyone, I will go through the argument. What we have done is the following. We have taken a finite rank of the statement is T is in the closure of finite rank operators. Then T is weak norm continuous. We have taken a operator, finite rank operator S, which is epsilon close to T. Okay. Then we have taken a weekly continuous analysis. Then we have taken a net x lambda converges to x weekly. Then sx lambda converges to sx in weak topology. But then that is equivalent to saying sx lambda converges to norm topology. Then using this inequalities, we get that tx lambda converges to tx in norm. Okay? So tx lambda converges to tx in norm. I mean, T is weak norm continuous. That's what we have. Okay? Now, 2 implies 3 is trivial. H1 is weakly compact by Banach-Alacoulou theorem. Okay. So T is continuous. T is weak norm continuous. So this implies T of H1. H1 is compact. Okay. T of H1 is compact. No. That's all. You don't need to take it. Okay. Now 3 implies 1. Okay. So what is 3? 3 is, we are assuming that T of H1 is compact with respect to norm topology. And you take the unit ball and the range of the unit ball is compact with respect to norm topology. Then there exists a finite rank sequence of finite rank operators which approximates T. So we have already seen that finite rank operators are strongly dense. We don't even need it. We can take that P and whatever. And we can take T. Okay, choose. So we are assuming T of H1 is compact. So, okay. T of H1 is compact in non-topology. Okay. Then we want to prove that T is in the closure of finite rank operators. Okay. There exists finite rank operators. So let Tn, let's forget about that. Let's take let Pn converges to identity in strong topology. Okay, in strong topology. Okay. And I want to say that the claim is Pn, which is finite rank. I mean Pn finite rank operator. Pn finite. Okay. Pn finite rank operators. Then Tpn converges to T in norm topology. Okay. Why is this true? So suppose not. Suppose this is not true. That is Tpn does not converge to T in norm topology. What does it mean? Given, what does it mean? This means there exists an epsilon naught. This does not, I mean, that is Tpn does not converge to the suppose not, that is Tpn does not converge to T in. Then there
But did you mean to say that like units pair in H star, like did you mean to say H1 or H1 star?
H1. What do you mean by H1 star? H1 and H are it's reflexive.
Oh, okay, okay.
Asking H is reflexive because the compactness you are asking.
Yeah.
Yeah, H is reflexive. So weak topology, weak star topology coincides.
Mm-hmm.
H is its own dual anyway. I mean, up to it's not a linear isomorphism; it's an anti-linear isomorphism. Okay, H is its own dual, so it's compact. Okay? So then there exists epsilon naught. There exists an epsilon naught greater than 0, such that for all k in natural number, given any k, there exists there exists what? EPK. And we have to say that such that given any pk, there exists a nk. There exists an nk. For every k, there exists an nk. I mean, there exists a subsequence. That's what I want to say. There exists a nk in n such that t p nk minus t is greater than, right? This is what is true now. I mean, given any k, there exists something greater than that, such that t p n k, there exists given any k, there exists a nk greater than that k, such that t p n k minus t is greater than epsilon. Okay, I mean, there exists a subsequence that this is greater than epsilon. That's what it means, right? This is a increasing. I mean, this is nk increases to infinity. Okay. There exists a subsequence such that I mean this is clear. Okay, this is what the negation of convergence is. Okay. That is, there exists a x and k in H1. So what does norm mean? Norm is just the supremum over the supremum of the whatever the operator we have acting on the unit ball. So there exists x and k in the unit ball such that t p n k minus t x and k is greater than or equal to epsilon. That's what it means. The supremum is greater than. Okay, is greater than epsilon. Okay. So we want to get a contradiction because of that. But then x and k is contained in H1. Okay. So t x and k, which is t x and k contained in t H1, which is norm compact. That's what we have assumed. Okay. That's what you have assumed. T H1 is compact with respect to the norm compact. So there exists another subsequence which we don't want to. I mean, we have to. So without loss of generality, if needed, I mean, without loss of generality, we are just going to use a subsequence. That's okay. Assume t x and k is convergent. Converge to t, some converge to some. I mean, we have to take further subsequence, but we will assume that we are using that subsequence here. Okay. I don't want to use another notation. Okay, without loss of generality, assume t, this converges to this. Okay. Okay. Now what do you want to do? Now we want to take t, which is just 1 minus p n k minus identity t acting on x and k, which is greater than epsilon naught. Okay, which is greater than epsilon naught, which is less than or equal to. So what do we have? We want to say that I want to use the value. Tx and k converges to that now. So Tx and k converges to but it will converge to some tx. I mean, it's in th1, no? So it will converge to some tx, right? I mean, it is in th1. th1 is the compact. Okay, so it will converge to some tx. It's not some. It converges to some tx. You assume that y equal to tx. Okay? I mean, we are using the fact that th1 is compact. Okay, so tx and k is in th1, and it will converge to some tx. It is still in the range of t. Okay, some tx. So this is less than or equal to p n k t x n k suppose I want to get x minus minus identity. What do you do?
So like T should be before P and K minus identity, right?
He should be
The left side of P and K minus identity.
what's your question?
Like,
Here you should be here.
yeah,
It just doesn't matter whichever the way. I mean, both way it will converge. No, it just doesn't matter which way you write. Both will converge to that. Oh, here I have written it like that. That's why you were asking. Okay, okay, it doesn't matter. It just doesn't matter whichever the way you write. You take there, it's the other way. I think I want it this way. So, let me come to that one second. Let me write the right triangle inequality. I have to apply triangle inequality. So I have to get somehow that use this fact tx and converges to this. So tx and k. Now what do you have? X and tx and k converges to. This is okay. Tx and k. Tx and k minus identity. Tx and k minus x. Okay. Plus what do we have? We want to show that something goes to 0. Okay. So t so y minus p lambda y. What is the p of tx lambda? I mean, this should be very simple. I don't know why I'm doing it. P and k minus identity times y. Or identity minus this, whatever. This is less than or equal to identity minus p and k. P and k minus identity. Identity times t x and k minus tx. Or you can use y itself. I don't think there is any problem. Plus times. This is just, okay. Let's take just this is equal to y. There is no need for tx. Okay. So this is y. But then you will get only y here. No? Is that right? What I have written. I've just added this y and I have subtracted this y. Yeah, this is okay. Tx and k converges to this. Yeah, this is okay. Okay. Now p and k converges to identity strongly. Okay, so this goes to 0. For all y, this goes to 0. On the other hand, tx and k converges to y in norm. So this is less than or equal to norm of p and k minus identity times norm of tx and k minus y plus norm of p and k y minus y. Now this is, I mean, this has norm equal to 1. P and K is a projection, identity is a projection, but identity is a bigger projection. So this has norm 1. Okay, this is equal to P x and K minus y. This goes to 0. And P and K y minus y. This goes to 0. This is done. I don't know why I was confused. This fine? And just using the fact that it is, you can do it for using nets also, okay? And just avoiding nets. The same proof will work. This is okay. Shall I go through it again? Okay, let me go through it again. So we want to prove 3 implies 1. So what is 3? 3 is, if H1 is the unit ball in the Hilbert space, then T of H1 is compact. That's what we have. That's 3. Okay. Then we want to prove that there exist finite rank operators which converges to T. We take Pn finite rank projections, some finite rank projections, or we can take the same Pn which we used earlier. Pn converges to identity. Then Tpn converges to T in norm. Okay. Then our claim is Tpn converges to T in norm. That's what we want to prove. Okay, so we want to prove that Tpn minus T is goes to 0. Suppose it does not go to 0, then there exists a subsequent such that this happens. Okay, and subsequent such that this norm is greater than epsilon 0 means there exists a x and k such that this is greater than epsilon 0. Okay, but since x and k are contained in the unit ball, T x and k has a convergence subsequence because T of H1 is compact. Okay. Now we take that convergence subsequence, then we just use the triangle inequality to prove that this goes to 0, which is a contradiction. Okay. Because it's greater than epsilon naught. We have assumed that this thing is greater than epsilon naught, but this goes to 0, okay, which is a contradiction. That's all. So Pn, Ptn, whatever the Pnt. I mean, we assume that Pnt does not converge to T in norm. Then we got a contradiction. So Pnt converges to T in norm. So that is the proof. Okay. Is it fine?
Yes, sir.
Okay. So, okay. So these are the 3 equivalent conditions. Any operator T satisfying this condition. Any T V of X satisfying one, either any one of the condition 1, 2, 3, or if it satisfies one condition, it satisfies the condition. Satisfying 1 to 3 is called a comparator. This is called as a comparator. So a compact operator is something which is, which is a limit of finite rank operator. You can take it, or it takes the unit ball to compact. Unit ball to norm compact subset. Okay, but then that means that it will take any bounded subset to compact subset. Okay, relatively compact. If it is closed and bounded subset, which any closed bounded subset is weakly compact. Okay, in the Hilbert space. So T of that is norm compact. So it will take any bounded subset to relatively compact subset. That is what a compact operator is. So this is the definition of compact operator. I will see whether I prove spectral theorem for this compact operator in the next class. I think I will prove it in the next class because that's not very difficult. Since we have time, we will prove for compact operators. Then we will do it for general normal. We can prove for general normal operator, then get it as a special case, or we can prove it directly also. Because since it's not very difficult and since we have enough time, we will do this. Okay. So I will stop here. If you have any questions, you can ask.
Sir, but the proposition which you had discussed earlier regarding that norm continuous, weak continuous, those being equivalent.
Right.
So does that hold for maps between Banach spaces as well?
Yeah. Yes. Yeah. You have to write it appropriately. Banach basis means you have to be very. No, I haven't checked, but it should.
So,
work.
for example, one thing that this result that this weak norm continuity and the compactness of the operator being equivalent. So, for in general Banach spaces, you need to assume that your Banach space is reflexive for that to hold. So, I was just wondering if that thing goes forward.
See, we are using some sort of inner product which we can still use. No. Why do you need reflexiveness? You are using only weak topology. For weak topology, it will work. I think it will work. We are using inner product or the existence of the adjoint. That's what we are using. Okay. Then
I mean, I had seen a proposition in a book where they said that if the Banach space is reflexive, then this weak to norm continuity is same as being a compact operator.
no, I am not talking about weak norm continuity. The earlier proposition you asked about that. I think that follows.
Oh, yeah. Okay.
You are asking this proposition or the
No,
compact
actually,
operator, you can define our Banach space also. Then you need to assume. I mean, since you have to differentiate between weak and weak star topology. See, here we are using weak topology. I mean, we are using the compactness. So if it is reflexive, then weak compactness and weak topology and weak star topology coincide. So that is why you need. I thought you were asking about the earlier proposition.
so yeah, earlier also like
Norm continuity is equivalent to weak continuity.
And that is true for any Banach space.
I believe so, because we are using inner product kind of thing, which you can write it in terms of, I mean, the same inner product you can write it using linear functionals, and you can define the adjoint precisely. We are using the existence of adjoint, and we are doing some manipulation using adjointness. Okay, so that will work. I think that will work. I don't see any difference. I mean, you have to write it to check each and every person. I think
Okay.
Okay. But for use this compactness property, you need reflexivity. Okay.
Okay. Yeah.
Goodbye.
Thank you.